So let's pick up from where we started with our patch surface. We have a randomly created patch surface that we're going to treat as a topography. Hopefully you've had a chance to play with the different seed values, see what that creates. Let's look at a couple of different ways that we can operate on this surface as a way to deal with its representation. So the first and most obvious one is contour. So I'm going to double click and search for contour, and we are going to take a contour from a B-rep. A B-rep in Grasshopper stands for a boundary representation, which is a surface, and so we're going to contour a B-rep. Let's look at the inputs that it needs. It needs a B-rep or a mesh to contour. This will be our patch surface. It needs a contour start point. This is defined as 0, 0, 0. And depending on what you did with your domain for your z value, you may want to increase these, because if you have a point or if you have part of your surface that's coming down like it is in mine, and if that's below that point, it won't contour it. So what you can do is just move your start and end domain for the z up, and then we can make sure that we can just use this simple default as the origin point for our contour line. And so that start point is set 0, 0, 0. We can change that if we need to later. Contour direction is 0, 0, and 1, and so that's in the z direction. So that's also the default. All we need to set is a slider for our distance. And so I'll set this 0 less than 5 less than 10. And we'll plug this in to the D. And we can see that we just got some initial contour lines. If we turn this down and get to be more like 1 foot contour lines, this is beginning to look more like a topography. That looks great. So let's deal with representation a little bit. And so let's see, because I want to control what this looks like and I want to hide that point, let me build my own. And so that's probably the plane where our contour start point. So let's just build our own point. And so we can do that by constructing point. Construct point. Plug that in for P. Now we can hide it. Right click and hide that point. So the other thing that we can do is to start using some of our custom, so under display, preview, there's custom preview. And we can do two things with this. Custom preview, we can see it has the jagged edge. There's nothing that comes out from the custom preview. And then we can use a swatch, which is a color swatch. And so let me set this to maybe a greenish color. And accept. We'll plug this in for material override, and then I'll turn the patch surface to have that as a color. I can hide the patch surface now because I have that preview as an output. And then I'll also color the contour lines. So if I copy my preview and swatch, I can turn this swatch into black, and then set the contour lines for that geometry and hide the contour. So now I've got a topography with contour lines. So I hope that makes sense. Go back, change your seed values, and let's see if that continues to work. So now we have a representation of that. So that's one type of representation that I wanted to cover. So that's contour lines. So what we can do is pull all of this down and group it, and we can name it contour. And for now, we can hide the preview of both of those. And if we want to come back to it, and this is something that we'll continue to work on this semester, is that what's amazing about these digital technologies is that it can have multiple and simultaneous different types of representation associated with it. And so we can continue to have the contours running in the background, but we can have a couple of other representations that come with this. So the next thing that I want to do is I want to make it so that we could say 3D print this as a base model. And so what I'll do is I'll come back, I'll turn on the patch. And the way that I want to approach this is I want to extract the boundary. I want to project the boundary down to the 0 plane. And then I want to build a solid and turn this into one solid object. And so there's a couple of steps that we'll use to do that. And let's see, we will find the edges. So under surface and analysis, there's B-rep edges. So let's bring this in. Our B-rep is our patch surface. You can't really see it, it's really pale, but there's now just a green line around that. We want to use the top element from this, which is the naked edge curves. So once we have those edges, we want to do a couple of things with it. First, we want to project that down. And it's maybe easy if we hide our patch. Now we can see that boundary condition. And let's project an object onto a plane. And again, this defaults to a plane at 0, 0, 0. And let's connect this to here. And now we've got that. And so what I want to do is I don't want to get too far into any data structures, but I know that this can create some issues at this point, is that if I output this to a panel, I've got 4 curves. And the way that Grasshopper works is that 0 counts as the first one, and so it's 4 curves, but they're numbered 0, 1, 2, 3, 4. I'll copy the panel. Let's look at this geometry. Now there's 4 planar curves. So what I want to do is to build a loft between them. And let's see what this looks like. Loft. And what we'll do is we'll just feed one in. I knew this was going to happen. And so what's happening is that the data structure, we can see the difference between, well, we can see that there's a list. And so the shaded part at the top is a kind of container for multiple lists. Watch what happens if I'll do this as an external tool, under sets, and we graft the tree. And this can also be done. We can right click on these and we can find graft. But for now, when we're starting out, let's take this. And so this graft then, maybe I'll do it above. When we graft it, look at the difference in the data structure. And that now we have one curve within each list. So we have 4 lists within this structure, each with just one curve. So when I feed this into project, the same thing happens over here. And so what happens now when we give these 2 things the grafted edges to the loft and the projects that are grafted to the loft, now this produces, it knows to take one edge and one projected edge, another edge and another projected edge, and it can match those up because they're split, because they've been grafted. I don't want to cover this in too much detail right now, but I hope that makes sense, is that those edges, rather than just treating it as one continuous curve, we can treat we can loft between each of them, and this works. We want to do a couple more things, or one more thing, is that we want to build a planar surface on the bottom. And so the way that we'll do that is that's also a surface and a freeform surface. It's a boundary surface. So we can get boundary surface, and we want to take our projected edges and feed it into this. I think it doesn't, it wants one simple thing. So let's just try and flatten that, and that works. And let me undo that just so that you can see. I'll undo that flatten, and we can do that with sets again, under tree, and where did it go? Flatten tree. In the top right is that. I'll add a couple panels again. Coming out of the projected lines, because we grafted this, this is in 4 separate curves. And when we flatten it, because that's what boundary wants, let's see, we'll bring the project into the flatten into here. We can see that we get just the 4 boundary curves. When we feed this flattened object into the boundary, we then get the flat surface at the bottom. It seems like a couple of steps, but we're just trying to work through in a kind of simple, rigorous way of how would we build this. It seems like a lot of work, but the payoff, right, if we were to do this just one time, we would just do these steps. Sorting out the data structure, sorting out this sequence allows us to then go back to the beginning, change these seed values, and allow this to produce a number of different options for us. So we've got our patch surface, our loft, and our boundary. And let's just create a join, a brep join. And I think we might have to flatten loft, so that when we bring all of these together to join, it'll be our edges, holding down shift, our boundary, and then our patch surface. We have to hide everything else. And here's our join at the end. So what we have now is a solid object. It's completely closed. And what we could do now is to, let's see, this is something that could be 3D printed. And so this is a kind of simple thing now to come back to and allow this to work. We could turn back on our contour lines that are just on that surface, so we get a sense for that. We could also contour this in multiple directions. You could, rather than contouring it from bottom to top, we could contour it left to right. We could start to cut sections in it that way. But this is the second representation. And maybe what I'll do is I'll just grab my preview. So I'll Control C, Control V. And let's make a preview of the join. Give it a slightly different color. You can hide the join, and we'll turn on the preview. We can hide our patch again. So now we have something, we could 3D print this. We can have a representation of something that has a little bit more mass to it. And we can come back. Remember, this is the important part, to be able to come back to the beginning and modify this using our different seed values to produce possible topographies. So that if we have one that we like, that's good. The third and final representation that I want to look at is just being able to break up that surface into a series of patches and color code them. And we'll use this over the course of the semester. I like being able to leverage these tools to give us some additional information as we're making design decisions. Something is color-coded, it tells us something's wrong, it gives us a dimension, it can give us other things through the color coding. So let's hide that preview. And we can hide the contour lines for now. Again, we can come back to any of these. And let's come back to our patch surface. As I do that, why don't I group this together? And let's just name this solid site. So let's move and we'll work our way up at the top. So the first thing that I want to do is I want to ISO trim the surface. And so this is something we just type ISO and there you go, ISO trim. This will allow us to take our surface and split it into a series of smaller patches. And this way we can start to color code those individual patches. And what we need for this is a surface. We'll take our patch surface and plug that into S, and then we need a domain. This is a slightly different domain than what we've been using before. This is a two-dimensional or a two-directional domain. So let's look at construct domain squared. Create a two-dimensional domain from 4 numbers. Actually, you know what we want is divide domain. Because we have the domain of the surface and we just want to divide it. And so we're going to have a couple of inputs to this. We're going to, the I at the top of this is our base domain. That's going to be our patch surface. Then we can have a U and a V. So let's just make a slider. This will be 10 less than 20 less than 30. And we can feed this into the U and the V. And U and V are just the way that we work with the surface, the way that that gets divided up, U and V in those two different directions. This goes back to the earlier reading that we had. This is a NURBS calculus surface, and so that's why you get U and V traveling across that surface as opposed to X, Y, and Z, which are Cartesian coordinates. So we take this divide, we plug it into our surface, and now we can see we get this smaller grid on there. And so if we want to increase those, we can. If we want to decrease it, we can turn it down. So something, there's a high enough resolution of our surface patches there. We'll turn off, or we'll hide our patch. So we just have that now. So now the next tool that we're going to use is that we're going to use area. And it sounds like a strange tool to use, but area does a couple of things for us. It has geometry that comes in, so we can feed this in, and you can see it just added a point at the centroid of each of those subdivisions. And so while we can get the area of each of those smaller patches, we can also get the centroid. And so the centroid is the thing that we want to grab. And let's see. From the area, I want to deconstruct each of those points, because where I'm going with this is that I want to use color to color code the height of each of those panels in the Z value. And so now that we have those individual points at each of those smaller subdivisions of the surface, I want to find the Z value of that point. And the way that we can do that, we built points earlier by putting in X, Y, and Z values. Now we have a point we can extract X, Y, and Z values. And so this is under deconstruct. Deconstruct a point into its component parts. And so we take the centroid of that point, and then we're going to pull the X out of this. or sorry, the Z value out of it. And so we have that. Where I'm going, just kind of go along with me. I watched a tutorial, figured out these components, figured out the order. It's not necessarily intuitive in terms of what we're doing, but what we're going to do is we're going to extract each of those Z values. We're going to plug it into a range, and then we're going to color code that range in a different color representation than we've seen before. And so the first thing that we're going to do is get the bounds. And so bounds, so I'll bring up some panels again so you can see what we're doing. What was that? Panel. And so the Z values that are coming out of those deconstructed points are really just a list of values. And these are their heights. Remember, these heights should correspond to what our domain was within here, but again, I saw some values that were greater than 50. Remember that this domain is the points that we started with. The surface may swell and shrink as a way to capture those points. And so while the maximum domain of our Z value here for those points is 48, it looks like we have some of the Z values of some of these other points are 52, in that kind of range. So this is the list of all the Z values for every single one of those centroid points. The bounds then, no data was collected up, sorry, so we never plugged this in. The bounds give us the min and the max of all of those values. And so 52.64 is the highest, and 25.07 is the lowest. It's a really simple little component called bounds that just gives us that min and the max. And so what we want to come back to now is we're going to use one more tool that's called Deconstruct Domain. It looks like this, and we're going to feed in the bounds, and look at what this gives us. This will give us the range. Well, it gives us the same range. So from U and V. Actually, you know what? That's not the right deconstruct domain. This is the right one. So we'll bring the bounds into this, and we should get start and end. So start will be the low value, end is the upper value. So now we have that boundary. We have the min and the max of that domain, of those deconstructed points. And so the last thing that we're going to do is plug this in to a preview. Let's do this from display, custom preview. The geometry that we're going to custom display is our isotrim, which is all the way back to here. But what we want to do is use preview, let's see, color, graphs. I want to use, let's see, a gradient. And so the gradient is under inputs, under parameters, inputs, and then gradient right under color swatch. And so gradient allows us to do a couple of things. We'll plug this in to the material, and then we're going to plug in, we have 3 inputs to this. We're going to plug in the start and the end, and then the value that we're actually getting is going to be the z. Let's just change by right-clicking that point. We can change the color. I just want to do, maybe I want to flip-flop these. What I want to have is that maybe we'll move from one color that's low. So maybe we'll set a low color to be blue and a high color to be red. And let's turn off a couple things while we're here. We can hide these. So this is giving us now a third representation type that gives us the z value. So let's say that the altitude mattered where we were within the topography. And so now we're color coding with the kind of contours as we move up. And so the low points down here are blue, and as we move up, it's red. You can see that we can also slide these and get a really, almost no gradation between them. But let's say we really wanted to identify one low value. Where's the lowest point on that overall surface? It's down there. But I do like the overall gradation. So we can even move the points to the very edges. And then as we go back and change our seed values, and these right now, those the values of that diffuse color are always changing, because remember, the points are moving, and so this is taking the boundaries of the min and the max. We could set these values, let's say, to give it slightly different values. Let's set, let's disconnect the low value, and then let's see what happens when we set it to 0. Nope. And so it's just kind of blue down here when it's set to 0, because 0, if we come all the way back to where our solid model was, 0 is all the way down here. And so, but this will be if it's always going from 0 and always going to the max, we could also change this slightly. And so we know then, of having that as an absolute value, that this will be consistent except for at the top. But we could also change that. Let's see, disconnect it. We'll set the upper limit to 40. Which is maybe in this range already, so maybe that needs to raise. We'll set it to 70 this time, and we'll see what happens. I have the hardest time setting those numbers with my mouse. So now we're getting a sense that we're in the mid-range because of that. But I don't mind the relative nature of these, so that the min and the max of our surface are always going to change. And so the minimum point is always going to be blue, the maximum point will always be red. So now as we change our seed values, that will always be true. So those highest peaks are going to be red, and the lowest values are going to be blue. Okay, so we have 3 different representations then. I want you guys to generate some surfaces. I want you to generate some topographies. I want you to play with the representation. And have some fun with this. And again, I'm putting the pressure on you to generate a number of different variations. And so this is the reason why we're not constructing these one by one as we go, but we can come back and use the seed values. The other thing that I do want to show you, let me just find a surface that I maybe particularly like. Is that we can hide this representation. We can come back to our solid representation. And if you're going to work back and forth between Rhino and Grasshopper, what we can do is we can come to the join, right click, and bake this geometry. We'll set it to default layer. Group it, although we shouldn't have to group it because it's one thing. We can see now that this just generated or created Rhino geometry. So this is what you see in light green is the Grasshopper representation. Within Rhino is the other representation. So we can take this, contour it, 3D print it, do anything we want. But here's a simple way. If you wanted to show, let's say for Studio, you needed to have a number of different options to share with your professor, or a number of different options to be able to show to a colleague. You can output these. And the only thing that I would maybe, I don't want to say caution you with this, is that you should mark what seed values they were in case you want to come back to it and work on it again, because we don't have any of that information saved once we bake it. Once it's baked, it's static, simple geometry again. But there are other things that we can do with it when we do bring it into Rhino. So if you wanted to, say, render an array of all of the different topographies that you've been working with, or massing models, or whatever they might be, that's a simple way, is to just extract them through baking as a way to do that. And what you might do is even label them with the seed values, so that if you really decided that you wanted to come back and work with this one, you could go back to Grasshopper, plug in those seed values, get that surface again, and then continue working on it in different ways. Okay, so hopefully this makes sense. I want you guys to play with those different options, change the colors, change the spacing, see what different options are available to you, and have some fun. So this should give you everything that you need to know for the second assignment. And as I said, within the lecture, I'll unpack some of these things. We'll talk a little bit about data structures. We'll look at how we might be able to deploy random numbers in terms of generating geometry and thinking about this as it relates to algorithms. So my hope is that this helps and that you've had some fun. And let me know if you have any questions. Thanks.